many people don't know me. I'm from Academia Sinica Institute for Physics. Me and my group, we are working on astroparticle physics. And so Francesca is currently a guest in my group, and we are working on astroparticle physics. And so Francesca graduated in 2020 from the University of Stockholm. And
KTH, Royal Institute.
Oh, KTH in Stockholm.
Yeah.
And she was working with an astrostatistician, among other actually instrumental works. And then she moved to the Excellence Cluster at the Technical University of Munich, becoming some sort of data scientist working with physicists. And since 2022, she is a Minerva young non-tenured fellow group leader at Max Planck for Physics in Munich. And so she has a small group of PhD students working with her, and her field is of extreme importance, I would say, for what I do. I'm interested in ultra-energy cosmic rays and in neutrinos, and since we have very few events, and you would not see anything by eye, the methods to analyze data and to interpret data using physical models, this interface between physical models and the data is extremely crucial. So Francesca is a specialist on this very rare field, and so I would ask you to welcome her and enjoy her talk. Thank you.
Thank you. Yeah, it's really lovely to be here. It's my first time in Taiwan, and I'm really enjoying it, so thanks for having me. And also for the nice introduction. So like Anatoly said, this talk is going to be all about cosmic rays. So these are charged particles that are accelerated to extreme energies, up to 10 to the 20 electron volts. And through their interactions, they also produce neutrinos and gamma rays. So we can use these different messengers together to try and learn more about the sources or where these particles come from. So we're interested in finding the sources because 10 to the 20 electron volts is very extreme. But these particles, in order to reach us, have to travel a long way through extragalactic and galactic space. And if we're lucky, occasionally they will slam into our universe at almost the speed of light. The resulting interaction of such a particle in our atmosphere creates a secondary air shower that leaves a signature of fluorescence light and also a particle footprint on the ground. And together, using these, we can measure these extensive air showers. And we have collected reasonable samples of events at extreme energy. So the question that we're all interested in is trying to figure out where they come from. The benefit of doing this and making astronomy with ultra-energy cosmic rays a reality will be a new way to probe extreme environments of astrophysical sources, including the very powerful and energetic environments around supermassive black holes. Additionally, if we can identify these cosmic accelerators, we can also use them to study particle interactions at energies way beyond what we're able to achieve here on Earth. Possibly probing also beyond the standard model and even candidates for dark matter. So before I get into how we're doing this, I didn't realize that Anatoly would introduce me, so I also wanted to make a quick self-introduction. I grew up in the UK, in Wales, and as you can see, I've been traveling around Europe for my education and career. And in particular, I did my PhD, which brought me to this topic of astroparticle physics and ultra-energy cosmic rays, which I did not encounter at any point in my education before that, so that was really exciting. And there, yeah, I worked mostly on the development of possible future space-based detectors for imaging these air showers, but also got into a little bit through working with these detectors and seeing the complex and hard-earned data that we have. I got very interested in data analysis. And so that led me to this postdoc where I actually really focused on statistics and data science and worked not only on my own projects, within astroparticle physics, but also collaborated with people in particle physics, cosmology, on different statistical challenges that they were facing. So now I have come back to astroparticle physics and is working towards multi-messenger astrophysics. And I'm trying to bring together with my small group at the Max Planck Institute for Physics these worlds of data science and ultra-high energy cosmic ray physics that I'll focus on in this talk. And yeah, right now I feel like these worlds are like quite far apart, and there's a lot we can do to bring them together, which can be, it presents a nice opportunity, but it's also a big challenge. So now I've said a little about myself, I want to go into more about how we actually try to do this, and the key physics that's important for doing this effectively. So I want to go back a little bit to the basics. The cosmic ray energy spectrum covers many orders of magnitude in both energy and flux. And we can see that this spectrum has quite a uniform power law shape over these large orders of magnitude. And I'm going to focus here on the higher end of the spectrum. And as we move to higher and higher energies, these particles become so rare that it's no longer possible to directly detect them. And we have to use this indirect detection concept that I showed in the beginning through the detection of these air showers in our atmosphere. And yeah, if we continue to higher and higher energies, we can start to see a little bit of structure in the spectrum if you look really closely. And the cosmic ray spectrum is normally described as a leg because it has a knee shape and an ankle shape. But more recently, we also start to see the possibility of a second knee. So this analogy is getting a bit weird. In general, we expect as we go to higher and higher energies, it's no longer possible for these particles to be confined for long timescales within the magnetic fields of our own galaxy. And so we are not sure, but we think at some point through this knee to ankle, there's a transition from where the cosmic rays we see are dominated by galactic signals to extragalactic signals. In particular, for this talk, I'm going to be focusing on the ultra-high energy cosmic rays, defined as energies above 10 to the 18 electron volts. That's really down here in the foot of the cosmic ray spectrum. And at these energies, the particles we detect are extremely rare, with fluxes that go as low as 1 particle per square kilometer per century. So you can imagine that we need very, very large detectors in order to accumulate reasonable samples of these particles, and we also need to wait for relatively long timescales, but not a century, don't worry. So just to put in perspective the kind of energies that we're talking about, the highest energy particle ever detected is really traveling at almost the speed of light with an energy of 3.2 times 10 to the 20 electron volts. And this has been termed the oh my god particle. In comparison with the equivalent fixed target energy we could achieve at the LHC, we see that we're already several orders of magnitude above this, opening up particle interactions that we can be studied like already much beyond what is capable in the LHC. So we know that cosmic rays are charged particles. So even at these high energies, they're very much deflected by the intervening magnetic fields between the extragalactic sources and us here in the galaxy. We expect in general 2 distinct effects. We think that our own galaxy, which has a larger magnetic field, will lead to relatively large-scale deflections on the order of 10 degrees. And it will also have a kind of coherent lensing effect. And this will be due to the region of the galaxy that the cosmic rays pass through as they propagate towards it. So we will expect some correlated and coherent deflection. On the other hand, as the cosmic rays propagate through the cosmic web, we expect them to experience many small-scale deflections that can add up as they propagate to scales of more like a few degrees. And while these effects are relatively small, they become more and more important the further the sources could be away from Earth. In addition to magnetic deflections, which obviously challenge us trying to figure out where these particles come from, we also need to think about the potential interactions of cosmic rays as they travel towards us. If you're traveling at almost the speed of light, the relatively low energy, calm cosmic microwave background becomes blue shifted and presents a formidable field to these particles, leading to a lot of interactions. This term is known as the Giza-K effect, after the authors who first proposed it. And what it really means is that at these ultra-high energies, we're presented with a horizon beyond which we can't expect to see particles, because they will lose energy through their interactions in the CME. This can be summarized as the idea of some loss length, which is the typical length scale over which particles lose energy. And we can see that as we get to higher and higher energies, this loss length becomes much, much smaller, and it's even on the scale of around 10 megaparsec or so. So in general, while this horizon is energy dependent, it also depends very much on the charge and mass of the cosmic rays. The typical scales that we're considering as origins of the particles we can detect on Earth are within, let's say, tens or hundreds of megaparsec at most. So coming back to this idea of multi-messenger astrophysics, cosmic ray interactions in their sources and as they propagate also lead to the production of gamma rays and neutrinos through photohadronic and hadronuclear interactions. So in particular, neutrinos present a very clear signal of cosmic ray interactions, and they're also produced with a typical energy scale of around 5% of the parent cosmic ray energy, presenting a rather clear connection. The picture with gamma rays, on the other hand, is a little bit more complicated because gamma rays can also be produced by electronic processes. So, for example, electrons being accelerated to high energies. And they're also absorbed, or can be absorbed, as they travel towards us, especially from large distances and at high energy. So we normally focus, for this talk, I'll only mention a little bit the cosmic ray and neutrino connection, but gamma rays can also be used here. I just won't have time to go into it so much. So these cosmic rays and neutrinos present a connected signal, but the different phenomenology means that it's not always trivial to put two and two together. So I'll explain this in a little bit more detail. So as I discussed, we expect cosmic rays to be deflected and interact as they propagate towards us. And this means as we try to figure out where they might have come from, we know that we need to take care of the impact of magnetic fields. And we also know that they can't have come from too far away, and we have to focus on the local universe. Neutrinos, on the other hand, are very complementary because we know that there's no deflections of these particles or significant cooling as they propagate. So they point directly back to their sources, and they don't really lose energy. But while this is also complementary, we are presented with another problem in that we have a very large horizon for possible neutrino detection. So even if we can pinpoint relatively well where this particle is coming from, it's very hard to understand what distance away it has been produced at. In addition, this large population of relatively distant sources can actually drown out the potential signal that we might hope to see from the most nearby sources and present additional form of background. So while we're probing different parts of the universe with these messengers, they're still very much complementary. And if we want to understand the sources of ultra-energy cosmic rays, we also need to think about constraints from neutrino signal. So moving now to how we detect ultra-high-energy cosmic rays through the production of extensive air showers in a little more detail. The primary particle will have some nuclear interaction with a air molecule in the atmosphere and produce a cascade containing muonic, hadronic, and electromagnetic components. And this cascade will evolve dynamically with time, growing, and then as the energy threshold is no longer crossed, the shower will become, again, smaller. And the end result of this, as I showed in the beginning, is both the fluorescence light from the de-excitation of nitrogen in the atmosphere, and also the particle footprint of this shower on the Earth's surface. And there's some other signals that I'll say a bit more about later. So the shape of these showers, which as we can think of as they propagate through some atmospheric depth in the atmosphere, can be analyzed in terms of the distance to the core of the shower, and we can see that the different components have different contributions here, and also the total particle number of the shower. And if we're able to get good measurements of this using a typical hybrid approach, again with the particle footprint and the fluorescence light, in particular, we try to image the fluorescence light in a stereoscopic way using multiple telescopes so that we can reconstruct a three-dimensional picture of the shower development. And this approach is what's currently used in the two largest ultra-energy cosmic ray telescopes that we have on Earth right now. And the particle footprint is measured with a large distributed array of scintillators or water Cherenkov detectors that can also then detect potentially muons and electrons, and the fast imaging to capture this flash, which happens on the scale of microseconds. It's also kind of new development to use radio to detect these particle showers. And some of us heard a talk on that recently from Kato, who's also here. But I'll focus on the standard approach here with particles and fluorescence light for today. The interaction of these, or the particles produced in these showers, also lead to the production of Cherenkov light, but this is not really practical to use as a detection mechanism as it's very beamed along the shower axis. But we do have to account for this light also if it gets scattered into the field of view of the fluorescence telescopes. So this hybrid approach is successful because it combines complementary aspects of the shower measurements. So these scintillator detectors that need to be distributed on a large flat surface have a very high duty cycle. They can operate basically all of the time, regardless of the weather. On the other hand, the fluorescence light, which gives you this 3D image of the shower, these telescopes can only really operate a fraction of the time. You need a dark, clear night in order to be able to really detect this signal. So while the fluorescence information gives a much clearer and calorimetric picture of the total energy of the shower, the particle detectors give a much higher duty cycle and give a larger number of events to the detected sample. Bringing these measurements together, we can reconstruct three quantities that describe the primary particle. The first being the direction. So using the geometry and timing of the shower, we can figure out relatively well at least the direction the particle is coming from as it hits our atmosphere. And then, not including the magnetic field issues, we can reconstruct these with an angular resolution of around 1 degree. The energy can be reconstructed by considering the calorimetric nature of the fluorescence field, and also the distribution and the size of the imprint of the particle shower. When joint events are available, these can be used to cross-calibrate and propagate this calibration to the larger sample of events that can be detected by the array. Another important quantity is the charge or mass of the primary particle. So cosmic rays are not only protons, but also possibly heavier nuclei. And the composition with current experiments is a challenging measurement to make. The quantity of interest here is the depth of the shower maximum. And basically for different compositions, we expect a different average depth of the shower maximum, penetration of the shower, and also subtle differences in the variation of this quantity from shower to shower. Because these differences are relatively subtle and have a statistical nature to them, it's currently only possible to reconstruct the mean and variance of X max for large numbers of showers. So if you perhaps bin up a number of events over an energy range, you can estimate the average composition of these events, but it's not currently possible to do that for individual events. So this approach is what's currently used successfully at the Piaget Observatory in Argentina and the Telescope Array project in Utah. So here you can see a little bit more realistic view of what's actually detected in these experiments. And in both cases, these have now been operating for over 15 to 20 years. So we've accumulated reasonable sample sizes of hundreds and even thousands of events at ultra-high energies. What this data looks like at the moment, we have the three different constraints that I spoke about. So first up, we can look at the distribution of the arrival directions of cosmic rays detected on a sky map, here shown in equatorial coordinates. And what we see here is that the arrival directions of cosmic rays are actually surprisingly isotropic. There are some fluctuations, and you can see a kind of large-scale anisotropy roughly here. But on the medium and smaller scales, it's actually only small fluctuations. We don't have anything that currently crosses the 5 sigma threshold with standard analyses. And this alone already presents some interesting constraints for a picture of these sources. We know that the deflections of these particles, if they come from nearby bright sources, must be very smeared out. And so we might expect that these particles are heavier than protons. Additionally, we can also look at the energy spectrum of cosmic rays. Here we see that at highest energies, there's still a lot of uncertainty in the details of the spectral shape because of the lower event rates, and also some disagreement in a systematic sense between the two observatories. That is still a topic of ongoing study that I won't go into so much here. But yeah, if one was to ignore perhaps detector effects, which I think still needs to be ruled out here, you could potentially use this discrepancy to argue that in the northern hemisphere, where the telescope array, this red spectrum, is measured, there's some source that is not present in the southern hemisphere, where the blue spectrum from Auger is measured. This is still speculation at this point. Finally, I also mentioned that we have some constraints on the charge or mass of these particles that are here shown again in this quantity, the depth of the shower maximum and its variation. And if we bin up our data sample into energy ranges, we can see that at the highest energies, it's not really possible to put these constraints. But so beyond 10 to the 20, for sure, we don't have anything really here. But what we can see is the trend at lower energies. So this depth can be compared with what we expect in simulations for a proton case in red and an ion case in blue. And we can see what we expect for both the mean and the variance. And in both cases, we see that the composition seems light at lower energies and then seems to become more mixed or even heavy towards higher energies. And so while we don't currently have really data-driven constraints at the highest energies, we can maybe imagine that this trend continues. And so this picture of heavier particles, which was not really what was expected when these telescopes were first built, is becoming a bit clearer. We have quite large deflections in the arrival directions of cosmic rays, and we see that the composition is maybe getting heavier and heavier at higher energies. And while somewhat surprising, it's perhaps not so shocking from a theoretical perspective, because the heavier and higher charged particles are generally easier to accelerate through some electromagnetic process.
So, can I ask?
Yeah,
so
please.
So I've never seen this map, but it looks interesting. So is that over density the direction of galactic center?
So I think this is the galactic plane,
There's a
and
star.
this is the galactic center, if I'm not
So it's
wrong.
not.
I think it's not obviously correlated with
Okay.
the galactic center. But as I mentioned, we wouldn't really
It's in A
expect...
direction.
Yeah.
Centaurus A.
At these energies, we wouldn't expect that these cosmic rays have some kind of connection to the galaxy. You know, it would be very difficult to accelerate them and confine them for macroscopic time periods. But yeah, essentially what we're looking at here is a visualization of the arrival directions that is shown by assuming each of them has a 25-degree radius deflection. So imagine stacking disks. And this is motivated, roughly speaking, from some kind of magnetic field modeling. But yeah, if we plot all these cosmic rays with these large disks, then this is where these kind of density over-densities are coming from, where the disks are overlapping.
So this is still expected to be heavily distorted by the galactic magnetic fields.
Also, yeah. So this is just the data smeared, basically. Yeah. So now coming to the topic of astrophysical sources and what astrophysical objects we think might be capable of producing and accelerating these particles. So we can use some very simple arguments to give a rule of thumb the kind of astrophysical environments that we're interested in. For example, if we want to accelerate particles, we will probably also need to confine them within the accelerator while we do that. So we can use arguments based on simple electrodynamics and the normal radius that if we want to do this, we need sources that either have a very high magnetic field strength or a very large scale. So on the first hand, we could consider pulsars as an environment where we have extremely high magnetic fields and very small scales. And then on the other hand, we could consider even large lobes of radio galaxies and even multiple galaxies and galaxy clusters as potential environments that have much larger scale sizes and weaker magnetic fields. So in general, if we want to achieve some target energy, say 10 to the 20 electron volts with these sources, it will be easier to do that with iron. We will need not so strong magnetic fields, large sources, and more challenging for protons. So again, coming back to why we think that the particles might be heavier at highest energies is mapped onto this HILAS plot here, which summarizes this criteria. And so I just highlighted a few of the sources that have long been candidates for ultra-high-energy cosmic ray acceleration, so like active galactic nuclei, gamma ray bursts, radio galaxies, and supernova remnants and other more galactic sources are typically seen as too weak to be able to power ultra-energy cosmic ray acceleration, but they are often invoked as the sources of cosmic rays in our own galaxy at low energies. So this very simple picture can give us a starting point, but there's a lot of very complex theoretical considerations that we need to consider when building models for ultra-energy cosmic ray acceleration. We're focusing here on extragalactic sources. We have a large zoo of possible cases. We have steady sources, possible transients. Models for these sources will depend on the particular emission zones. So an active galactic nuclei could have several different emission zones. And these sources will have some astrophysical populations that they're associated with, which have heterogeneous properties, different luminosities, evolution through cosmic time, and so on. We must consider not only the source environments around the sources, but also their host galaxies, if the galaxies are not the sources themselves. In addition, we also need to think about what happens once the cosmic rays escape the sources and all the propagation effects that I mentioned earlier. And that comes into the theoretical or phenomenological modeling of what can produce the signals that we see on Earth. So this situation presents us with an obvious challenge. We have a lot of complexity on both the theory side and also the data side through these indirect detection methods. And we start to see these challenges like manifesting in the analyses that we try to do in order to use the data that we have to study where these particles could come from. So here I just take an example from a recent work presented by the Pierre collaboration, where you can see here shown on these two sky maps, now in galactic coordinates, the prediction of two different models. One which proposes signals from Centaurus A, and another which proposes signals from a catalogue of nearby starburst galaxies. And what we see, if we look at the prediction in terms of arrival directions on the sky, is that the two look very similar. You know, there's this maybe faint addition here from the starburst galaxies, but in practice, if we do some simple analyses that focus on looking for correlations in the ultra-energy cosmic ray data, we're not really able to distinguish between these two pictures. And the methods that we're using are much more focused on rejecting the idea of isotropy as a kind of background or null hypothesis. And while we can see that the cosmic rays are kind of not completely isotropic, it's also difficult to really interpret, like, okay, what is behind these anisotropies? Especially if we just really confine ourselves to using the arrival direction data. This is not enough. An additional challenge that we start to see as we study these data sets and their possible correlations is that we see extremely energetic events, so the handful of events that exist at this very end of the spectrum, over 10 to the 20 electron volts. And an example of this that I show here is the so-called Amaterasu particle. When the particles get high energy enough, they get names. And yeah, this has been recently reported by the telescope array experiment. And if we just plot the arrival direction of this particle on the sky, here shown in equatorial coordinates, we see that it seems to come naively from an area of the universe called the local void, where there's a particular lack of possible sources and the matter distribution is particularly low. So while we have all these arguments about possible complexity from magnetic deflections, interactions with particles, it still presents a problem at some point because at lower energies and higher charges, we can have this quite large bubble of possible origins. The loss length of the particles becomes longer, they can come from further away, but they're also more deflected, so we get this kind of big volume of the universe. But as we get to higher energies and potentially also lower charges, this volume gets much more constrained. So we still need to, it's getting to the point where it becomes a little bit challenging to understand. So the solution that I present and that I focused on working on with my group is to address these challenges through advanced analyses. And in particular, we try and focus on characterizing signals rather than rejecting the background and understanding these signals that start to be appearing. And in order to do this, we need to have methods and models that have a large number of free parameters in order to describe the source physics, the propagation. And then we also use approaches that focus on goodness of fit, comparing models and observations. And I tend to take a more Bayesian workflow, which is a nice setting in which to do this. We can also use this to incorporate relevant prior information that we might have from theory or observations, not only of ultra-energy cosmic rays, but also in this bigger multi-messenger picture. So I won't go into too much detail on that, but just want to mention. In my group, we have a large range of projects also covering high-energy neutrino topics, but I just want to give a little impression, focusing today on the ultra-energy cosmic rays, of how we are addressing, for example, these two challenges that I mentioned. And yeah, I should not talk too much longer, right?
It's 1
How
hour.
much?
1 hour.
Okay,
Yeah,
I will not take that long.
No, you have like, let's say 15.
Yeah, it's good, yeah. Okay, so I want to start by coming back to this idea of the individual energetic events that start to puzzle people. And again, here I showed the Amaterasu particle, this time shown a different map highlighting this local void against the two-mass galaxy catalogue of the nearby universe. And as we see also in this density map, this void is really a three-dimensional hole that doesn't present any obvious source candidates, and even nearby sources tend to be also a little bit weaker, not so powerful, and it's difficult for us to imagine how they could be fitting our constraints on possible ultra-energy cosmic ray sources that I mentioned. So this got a lot of people thinking, if this is really the case, do we need more exotic explanations for the origins of this particle? And a lot of theories that have been kind of falling away in popularity became a little bit interesting again. However, in principle, we have to also keep in mind that because these particles have such deflected paths as they propagate towards us, what we detect at Earth, there's a long time delay between the emission at the source and the detection of it. So even if we struggle, we could dream up some astrophysical scenario here where there's a past transient that could have accelerated this event, and now it just looks like a kind of boring, dormant, quiet galaxy. But okay, this caught my interest, and together with a PhD student in my group, I thought, okay, if we don't have a good source candidate, why don't we use what we know about the ultra-energy cosmic ray propagation? We have very good models of this, to map out the volume of space that is really consistent with the observed energy and direction of this particle, and importantly, including all the uncertainty on our modeling of the intervening galactic magnetic fields and particle interactions, the stochastic nature of this. And also at this energy, we have really not any constraints directly on the charge of this particle, so that's a big uncertainty too. So we developed such an approach using a method called approximate Bayesian computation, which is actually really straightforward. What you can do with this method is you basically sample parameters that you want to learn about. So in our case, we take the location of the source in three-dimensional space as a free parameter, and also quantities like the true energy of the particle at the source, and the magnetic field strength and the exact realization of the magnetic field model can also be a free parameter here. So you sample a set from your free parameters of interest, you simulate a realization of what propagating such a particle through such a universe looks like. And here we use the CR Proper software. That's a very widely used Monte Carlo tool in the field. And then we basically accept this parameter set if the simulated data looks like what we see. So if this parameter set can produce a particle that looks like the Amaterasu particle, has a similar energy, has a similar arrival direction. And then we simply just like brute force this, run a bunch of simulations, and through this rejection process, we will build up an approximation, hence the name, approximate, of the posterior distribution or the probability distribution of the parameters of interest.
Excuse me?
Yeah.
So you mentioned the direction of this customer depends on the composition. Then how does this direction looks like for different composition, and how do you set the prior on the composition?
Yeah, it's a good question. So here you could imagine that if we would just think about it, the possible deflection of this particle, if we would try and go like backwards from the observation, is going to get bigger and bigger depending on heavier mass and higher charge particle. So we can imagine like, okay, for a proton, there's not much option at this energy, like the possible deflections are really minimized. But as this is relaxed to heavier and more higher charge particles, this can be much more spread out, right? So we want to quantify really what's the uncertainty here. In terms of setting a prior, ideally you would just say, I don't know, and use the full sky. However, this method is not very computationally efficient, and for this reason, for the work we've done so far, we had to make some assumptions. So we assume, based on theoretical arguments, that this particle should be heavier. For two reasons. Okay, one being just more theoretical, it's easier to accelerate a higher charged particle, so let's try with iron. Also because we're interested in exploring, like, what is the worst case scenario here, right? Like, people are saying it's from the local void. Is there any case of reasonable parameter space where this can be not true? So that drives the assumption of this analysis. In principle, if you can come up with more efficient method, which is some current work we're doing, then you could really leave it open and let the data bring a constraint. However, with one particle, your data is not super constraining. So here we need to bring together some assumptions, reasonable assumptions, and the information in the data, which is limited. So I talk about how to bring in more particles later. Hopefully that answers your question.
Yes, thank you.
So with this in mind, we have a prior, and our prior is kind of half of the sky in the end, let's say. So we expect that we explore this region of the sky as possible origin, and we say like, okay, from here we need really, really large deflections, so it's not so realistic with what we know about the magnetic field. With this prior in mind, our results look something like this. So we do get constraints that are smaller than the prior. If we just look at the total possible bubble of origins, we see that actually, thanks to the model of the galactic magnetic field and all the other uncertainties, we kind of shift generally outside of the local void. And some old source candidates start to be more plausible. So the sources, nearby sources, are listed here, with the nearer sources being larger and redder. So we see some options that are not unreasonable. And what we also do is, even though we assumed iron at the source, with our propagation simulation, we allow all different charges to be detected, because iron can disintegrate, also produce lighter particles along the way. And so we can also explore, like, depending on the detected particle's charge, what would these constraints look like? And we can quantify a little bit the picture I was imagining earlier, where for light particles like protons and helium, we would actually be pretty constrained in this local void, even if we had all of the uncertainties that we include. However, if we move to like medium and even heavier compositions, we actually open up a lot of possibilities beyond this. And like I said, for one particle, you don't have a heavy particle in particular, it's not very constraining. But one can imagine that in the future, if we could bring together lots of particles, larger data samples, that this volume would actually start to be constrained or have some kind of density map of the local universe. So that's where we'd like to take this, but for now we've been dealing with the computational aspect and only focusing on a handful of the highest energy events. With that motivation, we've also been working to, oh yeah, here I also wanted to mention that, yeah, there are other relevant free parameters before I go on that we can constrain, but again, with the single particle, we cannot put a big constraint on the energy or rigidity of the particle at the source. And the magnetic field parameters, we essentially sample a little bit from our prior. Yeah.
5 for me.
Okay, good. Perfect. Okay, so final project I'd like to mention is why I'm here in Taipei working with Anatoly and Keita also, is, okay, what if we want to use more than one particle? It's a good starting point. And also not only the arrival directions. Like earlier I was saying, the arrival directions alone are not really enough to describe the physics of the possible sources, and we can't really distinguish between different source models. And I tried to show this here by drawing weighted correlations here purely based on the angular distance between particles and sources. And then here bringing in more information where, okay, higher energy particles must come from more nearby and also have different possible deflections. And we can see that this changes a bit the picture of particle source association. In reality, there's a lot more complexity than just the energies and the distances. And we'd like to include this, what we know again about the propagation and the observations, bringing together not only the arrival directions, but also the energies and compositions, and for larger event samples. And in order to do this, we're going to have to make some simplifications to the model in order to make it computationally tractable, but we try to do this in a way that we only simplify the parts of the model that the data is not very sensitive to. So this is the aim of the game. For this reason, our data is not very charge or composition sensitive right now. So we make quite crude assumptions about the cosmic ray composition, splitting it into a set of 4 representative mass groups. And then we can construct a propagation framework that's based on the rigidity of these particles, so combined energy and charge. And this simplifies the picture a lot. So in this case, we can then perform simulations that map us from source rigidity and composition to a spectrum at the source. That's a function using the assumption of a certain mass group and a function of the spectral index. Additionally, we have to also consider models for the magnetic deflections, and we treat the magnetic extragalactic fields as a kind of smearing effect, like many analyses, and then we invoke a particular lens model to go from a sample of events at Earth to a projection of events and uncertainties along the galactic boundary. This model is simplified, but it still comes with a lot of free parameters. So I'm not going to go into the details, but the methods we used are based on Markov chain Monte Carlo, and in particular Hamiltonian Monte Carlo, which is particularly suited to exploring parameter spaces in high dimension. What we've done so far is applied this method to realistic data sets with large numbers of events from both the Pierre Auger and telescope array collaborations, based on sources that are currently being studied as prime candidates in both cases, so Centaurus A and M82. Interestingly, we see that if we project the event samples back to the galactic boundary, there's quite strong effects for the assumption of what we expect, intermediate mass group. And but with our framework, we're still able to correctly reconstruct the impact of the extragalactic magnetic field and also the source parameters, or the brightness of the sources. And what we've also been investigating is the importance of this charge information and trying to verify, okay, if we simulate intermediate composition, we're able to get a good reconstruction. But if we wouldn't know this and we would assume we have light or heavy particles, then we actually see how wrong that we can be and how biased our reconstruction is. So while we're still working on this, what we want to do next is fit combinations of mass groups. And that's what we're up to here at the Institute of Physics. And the goal and the outcome of this would be the most physics ever included in this kind of source analysis. So hope we can get some results. Yeah. Okay, so I was gonna talk a little bit about neutrinos, but I think I will skip. I just wanted to mention that recently the KM3net detected an extremely high energy event, which could potentially be like the first ultra high energy neutrino. But okay, it's one event, so we should not get too excited. In the future, there will be cool upgrades to the ultra high energy cosmic ray experiments. We'll get new constraints in the charge. This is the near future, like next year's. And improved exposure also from the TA. And yeah, next kind of big experimental projects will be beyond the 2030s. So it's a good time to try and make the data work. And yeah, these big future projects that are still very much in the planning stages will actually target both ultra high energy cosmic rays and ultra high energy neutrinos, which have not really been convincingly detected yet. So this joint neutrino cosmic ray picture will become very important. So finally, I'll end there. Cosmic rays have been, a puzzle for a long time now, but we do have serious samples of them thanks to big experimental efforts and using the Earth itself as a giant detector. We start to see the first signals emerging of sources, but it's still difficult to figure out what they are. And one way that we can attack these challenges is to include more complexity and more physics into the analyses that we do, so we can start to interpret the signals that we see. Thank you.
Questions?
This is maybe kind of a basic question, but you brought this up a lot, and I was a little bit confused. But why do you expect higher mass particles to be more easily accelerated and deflected? I would have thought naively that the charge to mass ratio being so much different than a proton would make it harder for it to accelerate, because for a given magnetic field strength, a larger mass would be more inhibited or something.
Yeah, good question.
I think the normalization is you're measuring the number of, let's say, 10 to the 20 EV, and then the mass per particle, if you divide by 50, is 50 times smaller. So if it's a single proton, then that proton would have to have 10 to 20. If it's an ion nucleus, it only has per particle 10 to the 2 times 10 to the 18.
I see.
Yeah, and in stochastic acceleration, the Larmor radius formula is 1 over charge there. So you need to, at the same rigidity, let's say 1 EV rigidity, iron nuclei have 26 times more energy.
Okay.
Right, so, but yeah, it's not always...
Yeah, I see your point. Not so intuitive, but I'm so used to thinking about it this way now that yeah, it's not...
Do you think on this plot? So how do we have an indication of which of these are the sources?
I would say no. Sorry, but I think like it's we still need to figure out.
I mean, except supernova remnants.
Yeah, this I spoke about a bit. This is too weak for sure.
Yeah.
I would say okay. I don't think we can really say conclusively like ruling out any of the other candidates shown now.
How about pulsars?
Okay, the pulsar case, we could argue it would be difficult to really produce the full observed flux of ultra high energy cosmic rays from pulsars alone, based on what we know about their populations. And in general, what we can start to do, given the observed isotropy, even though there's still, it's not a completely strong constraint because we have the unknown charge as a big free parameter. But we can start to say like, okay, the sources cannot be too rare or too bright because otherwise they would leave a stronger anisotropic signal in the arrival directions, and this becomes also complementary constraint. Yeah.
Is one of the future experiments going to resolve this definitively or unclear?
I think I would say it's unclear, in my opinion. I think having also the neutrinos produced, like co-produced by the propagation or interaction of the ultra energy cosmic rays, which we don't currently have, we have neutrinos at lower energies, would definitely help to constrain independently, or kind of constrain not only just possible sources but also the composition, which remains challenging. And it's my opinion that we can't really just collect larger event samples. This alone would not be enough. We need to have a much better constraint on what these particles are. Otherwise, it's going to be very difficult, as we see, to connect with the sources. That's my opinion.
Well, it could show up in data. You know, I mean,
and you can get lucky, right? Yeah.
I mean, right now we have this. So Francesca showed this large, the Auger sample, the last slides.
Yeah. Okay, let me go to this one maybe.
No, not this one. The events and Cato's plot.
Ah, yeah. This is nice.
So by now, so the previous one maybe. By now we
Yeah.
cannot discern any kind of pattern in it. Yeah, it's within significance is isotropic, but at the same time we actually cannot put the correct particles together according to the magnetic history. So particles that look like neighbors here could be actually tens of degrees apart because one is proton, the other is
This
ion.
is the key. Yeah.
So the one chance is if we identify the mass using advanced, machine learning methods, the stuff we're working on, and the other experiments,
New upgrades.
the current upgrades also work on it, and we can reanalyze the entire data that we have, and then, for example, remove the particles from which we know the deflections are big. And in that case, it could be that something shows up.
Yeah.
If it doesn't, it means, well, maybe, there is another decade or so it needs to pass, but also advanced analysis methods may also reveal something like that. Yeah. So we need to really search. I think some people say like, no, never, but I think I'm more. Well, we are more.
Mass constraints and neutrinos.
Oh.
But you cannot guarantee because we don't know what is producing them, so it depends then on the models.
For the localization of your very high energy event, there's a tiny bit of non-zero chance coming from maybe two.
Yeah.
Is that built in your forward modeling or?
No, actually, but I would say with this, it was interesting. We were trying to understand right here. It's a little bit of an artifact here because we are summing over all arrival compositions. And this part going up there is really coming from this heavier, in order to arrive, come from M82, we need very large deflections. So it ends up a little bit in the tail of this distribution that would assume that the charge is iron on arrival. And so it's somehow consistent with M82. I'd say the shape here is really coming from the galactic magnetic field model and what's allowed by that. But it looks like a little bit of an island here because now we've summed over all of them that it's just the way the distribution is normalized that what drops out.
So how well is this extrapolated magnetic field has been mapped? So what's the uncertainty?
Yeah, that's a really good question. So I don't have a nice plot for you, but there is a lot of uncertainty in that. It's typically handled in a systematic way. So we have a set of models that describe possible realizations of the magnetic field, and these are built using data from Planck and also line of sight constraints from radio sources. But it seems, in my understanding, this is not my expertise, that there are quite some different models or different structure in these models in terms of how they behave at the galactic center and how pronounced the spiral arms are and so on, that is allowed by the current data. So there's not one prevailing model that's very clear. And so in the analyses I've shown, we've always assumed one representation of this model, but if you would put in another one, in order to really quantify these uncertainties, you'd have to probably try a large number, maybe even around 10 different magnetic field models. And each of them will have its own structure built in. So this is also a challenge that we need to think about in the future, is how to bring those together in a reasonable way. But if we would identify a cosmic ray source, like each time we're getting closer to understanding the sources, we're also learning more about the intermediate fields, right? Like the study of one benefits the other. So there's quite a lot of cross-collaboration between these communities.
So you put a lot of effort into studying the Amaterasu particle, but in principle you could have taken any particle. It's just this is the one with the highest energy measured, right?
Science paper.
Yeah, it was like, it's kind of, it was
It's
a
a
bit of
fact-
fun, this choice, right?
Yeah.
Like, whether it's really the highest energy is kind of up for debate, because there's a lot of systematic uncertainty in the energy scales of the two experiments. So I think many people would argue that maybe it's not actually the highest energy particle, but was an arbitrary choice, let's say.
So no, my question is more, you said, okay, this is only one event. Is there, in principle, a way to associate other events with the same particle to make it a two-particle event? Or
So as in, try and find events that could have also come from a similar source?
something like that. Is there in principle a way to, or are there reasonable choices to say this particle, we assume okay, this particle can only come from one source. Is there a way in all of our other particles to find another particle that has come from the same source?
Yeah. In principle, you just need to extend the kind of modeling that we're doing. Exactly. But doing this, like computationally, what we did for this one particle, it's impossible to scale that to many. So what we're doing in our work with Anatoly and Keita is exactly trying to quantify the individual source particle associations and group them together. It's a kind of clustering. Is that maybe what you were thinking?
Yeah, I was just wondering what kind of how you can make this from an n equal 1 event to n equal 2 maybe.
So,
or is it like time the next particle detected, or is that
it's a little bit more
too dangerous?
Anatoly's worked on it. Yeah, the time part is hard. You have big time delays, right?
3 degrees is 10,000 years.
Yeah.
Yeah.
So you can start to think about this, but it becomes quickly very unconstrained. I think it maybe a little bit in the direction you're suggesting is also that if you imagine you didn't know the model for the galactic magnetic field, you could look for particles that have, I don't know, some kind of interesting correlations as a function of energy and try to map the galactic magnetic field, assuming that some kind of isotropic distribution prior to the galaxy. This is some kind of work that's also been done, but yes, it's difficult business.
So my other question was, you now pick this particle. Did you just for fun pick a random particle? And how would the uncertainties for a random particle with a much lower energy be? Would it be much more uncertain where it came from?
Yeah, so part of the motivation for picking Amaterasu was that this local void interpretation was bubbling around. There were a lot of papers coming out, like, okay, we need like the decay of some heavy dark matter particle to produce this. And so to me, I just wanted to highlight that actually we have so much uncertainty still that you cannot just like kind of eyeball this on the sky. And it became a nice case study. But the motivation for this method and trying to use this more data-different approach is actually coming from larger scale studies for correlations. And it seems that in a lot of no matter how you approach this, correlation study, it always seems that the high energy events are kind of left out. It makes sense because the bulk of the ultra energy cosmic ray data is low energy events, right? Like the spectrum is steeply falling. But the highest energy ones have a lot of constraining power. So I thought let's do an analysis that gives them some attention. Try to approach this from two sides, right? Like lots of particles with maybe less constraining power and individual particles with strong constraining power. Hopefully we can meet in the middle at some point.
So maybe last question, if anybody has one. Okay. Yeah, so if not, let's thank Francesca again.
Thank you so much.